There is a machine drifting through interstellar space right now, and the radiation out there isn't touching it. Voyager 1 crossed out of the Sun's protective bubble in 2012 into a storm of galactic cosmic rays, heavy nuclei flung from exploding stars, each one strong enough to punch through metal. Voyager doesn't care. It has no cells to shred, no brain to erode, no lungs to fail. It is the perfect interstellar traveller precisely because nothing inside it is alive. Now put people in that same machine. Those same particles start cutting tracks through human DNA, day after day, with no shielding that can stop them. The filters clog with no replacements coming. The air recyclers drift toward failure, one molecule at a time. And here is the part nobody admits. Building an engine that can reach another star may be the easy half of the problem. Surviving the space between them is something we have not even begun to solve. If you want to understand why the hardest part of star travel is not the launch but what comes after, go ahead and hit that like button and subscribe. Now, let's begin. Every conversation about interstellar travel begins the same way. Someone asks how fast we can go. Someone else calculates how long the trip would take. The numbers are staggering, the distance is humbling, and by the end of the discussion, the conclusion is always the same. The problem is getting there. Speed, distance, propulsion. These are the words that dominate every public debate about traveling to the stars. They fill every documentary, every conference panel, every comment section arguing about whether humanity will ever cross the void between solar systems, and they are all focused on the wrong problem. The assumption hiding underneath every one of those conversations is that if you solve propulsion, you solve interstellar travel. Build a fast enough engine, accelerate a ship to some meaningful fraction of the speed of light, aim it at the nearest star, and the mission is essentially complete. Arrival equals success. But that assumption is wrong. It is not just slightly off. It is catastrophically, fundamentally wrong. Because the moment a crewed vessel enters interstellar space, the propulsion problem ends, and the survival problem begins. And the survival problem is worse. This is not a matter of opinion or speculation. It is a matter of engineering, biology, and thermodynamics, all of which have hard limits that do not bend because the mission is heroic. Reaching interstellar space requires solving one enormous challenge: generating enough energy to push a vessel across trillions of kilometers. That challenge is extraordinary. But surviving inside interstellar space requires solving hundreds of challenges simultaneously, every single day, for decades or centuries, with no external help, no resupply, no rescue, no second chances, and no margin for error that would be considered acceptable in any engineering discipline on Earth. The ship must be its own planet, and planets do not run on spare parts. To understand why survival is the deeper problem, you first have to understand what interstellar space actually is. Not the romanticized void of science fiction, where stars drift past the windows like distant lanterns. The real thing. The physical medium between stellar systems that makes up the overwhelming majority of our galaxy. Start with what you lose the moment you leave our solar system. Earth sits inside a protective bubble created by the Sun called the heliosphere. The Sun constantly blasts charged particles outward in every direction, a stream called the solar wind. This wind inflates a vast magnetic bubble around our entire solar system, and that bubble deflects a significant portion of the galactic cosmic radiation that floods the rest of the galaxy. The boundary of this bubble is called the heliopause, and it sits roughly 18 billion kilometers from the Sun, about 120 astronomical units out. Voyager 1 crossed the heliopause in August of 2012. Voyager 2 followed in November of 2018. Both probes immediately detected a sharp increase in the density of galactic cosmic rays, the high-energy particles that originate from supernovae, neutron star collisions, and other violent events scattered across the Milky Way. Inside the heliosphere, the solar wind partially shields everything within it from this radiation bath. Outside the heliosphere, that shield vanishes. You are naked to the galaxy. But here is what most people miss about the transition from protected space to unprotected space. It is not instantaneous. It is not a clean boundary you cross in a single dramatic moment. Leaving the solar system is itself a survival ordeal that unfolds over years or decades before you even reach the interstellar medium proper. The heliosphere is only the first boundary. Beyond it lies a vast, loosely defined region of gravitational influence that our sun still claims, the Oort cloud. The Oort cloud is a theoretical shell of icy bodies, comets, and frozen debris left over from the formation of our solar system, extending outward from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. The outer edge of the Oort cloud sits approximately 1.5 light-years away. At 5% of light speed, a departing vessel would need roughly 30 years just to clear this region. At 1% of light speed, which is closer to what near-term propulsion concepts might actually achieve, the crossing takes 150 years. During this entire transit through the Oort cloud, the ship is already beyond the heliosphere's radiation protection. It is already exposed to the full galactic cosmic ray flux. It is already accumulating material damage, biological exposure, and maintenance burden. But it has not yet reached the true interstellar medium. It is still, in a meaningful gravitational sense, leaving home. The survival clock started ticking the moment the ship passed beyond resupply range, which for practical purposes is within the first weeks of the mission. Every degradation process described in this video, the radiation, the mechanical wear, the psychological strain, the life support drift, is already running during the decades it takes merely to exit our own sun's gravitational neighborhood. This is a detail that almost never appears in public discussions of interstellar travel, and it matters enormously for mission planning. The journey to the nearest star is not a single transit across 4 light-years of interstellar void. It is a decades-long exit from our own solar system's outermost territory, followed by a decades-long crossing of the interstellar medium, followed by an approach phase into the destination star's own gravitational domain. The ship must survive all 3 phases consecutively. The survival burden begins long before the ship reaches the emptiness between stars, and it does not pause or lighten at any point along the way. There is no coasting phase where the crew can rest and the systems can recover. From departure to arrival, the clock runs, the systems age, and the margins shrink. The ship is not merely crossing a distance, it is enduring a duration, and the duration starts the moment it leaves Earth orbit. This is not a subtle change. NASA confirmed through Voyager data that the galactic cosmic ray intensity rises significantly once you cross the heliopause. The heliosphere suppresses incoming galactic cosmic rays by roughly 20 to 50%, depending on solar activity cycles, meaning that outside its protection, the full unmodulated flux strikes everything in its path. These are not ordinary particles. Galactic cosmic rays include fully ionized nuclei of heavy elements like iron, silicon, and oxygen, traveling at substantial fractions of the speed of light. A single iron nucleus at these energies carries the kinetic punch of a fast baseball concentrated into a space smaller than an atom. When these particles strike biological tissue, they do not merely pass through, they shatter molecular bonds along their path, leaving a trail of broken DNA, damaged proteins, and dead or mutated cells. When they strike spacecraft materials, they displace atoms from crystal lattices, weaken polymers, degrade electronics, and accumulate damage that cannot be undone without replacement. And galactic cosmic rays are only the beginning of what interstellar space throws at you. The interstellar medium itself, the thin gas and dust between stars, becomes a weapon at high velocities. Even at 5% of the speed of light, roughly 15,000 kilometers per second, every hydrogen atom the ship encounters hits the hull with the energy of a low-grade cosmic ray. At 10% of light speed, the energy per particle climbs into ranges that produce secondary radiation showers inside the hull material. The faster you go, the more lethal the medium becomes. This creates a vicious paradox. Traveling faster reduces the total trip duration, which sounds like it should reduce the survival burden, but it simultaneously increases the radiation intensity striking the vessel. You cannot outrun the problem. You can only choose which version of it you prefer. Now consider the temperature, or rather, the absence of useful thermal energy. Interstellar space hovers at roughly 2.7 Kelvin, barely above absolute zero. This is not merely cold. It is a temperature at which most chemical processes halt, most materials become brittle, and radiating waste heat from the ship's systems becomes the only available cooling mechanism, since there is no atmosphere and no nearby thermal mass to absorb it. The ship must manage every watt of thermal energy it produces internally, balancing the heat generated by its power systems, life support, electronics, and human bodies against the radiation of that heat into a void that offers no buffer and no forgiveness. Get this balance wrong by even a small margin, and temperatures inside the habitat drift toward conditions that kill equipment or crew. There is also the matter of distance from help. This point seems obvious, but its implications are routinely underestimated. At the speed of light, a message from a ship traveling toward Alpha Centauri takes over 4 years to reach Earth, and another 4 years for a reply to return. At 5% of light speed, the ship needs roughly 85 years to reach that same star system. During that journey, round-trip communication with Earth stretches from months to years, reaching nearly a decade by arrival. Effectively, the crew is on their own from the moment they pass the outer solar system. There will be no mission control guiding them through emergencies. No resupply vessel catching up with fresh filters, new circuit boards, or replacement medication. No emergency evacuation if the reactor develops problems or if a disease sweeps through the crew. Every resource the mission will ever have must be on board at departure. Every repair must be performed with tools and materials carried from Earth. Every medical emergency must be handled by whoever is awake and trained, using supplies that cannot be replenished. The ship is not a vessel transiting between two ports. It is a sealed world that must sustain itself indefinitely with a finite budget of matter and energy. This is where the survival problem separates itself completely from the propulsion problem. Propulsion is a single engineering challenge, enormous and unsolved, but singular. You need a way to accelerate mass to high velocity. That challenge has a clear success condition. The ship reaches its target speed. Survival, by contrast, is an interlocking web of hundreds of simultaneous challenges, none of which can be allowed to fail, all of which interact with each other, and all of which get harder over time. Air must be recycled, water must be recovered, food must be grown or preserved, waste must be processed, carbon dioxide must be scrubbed, oxygen must be generated, temperature must be regulated, humidity must be controlled, radiation must be shielded, equipment must be maintained, spare parts must be available or manufacturable, medicine must be stocked, psychological health must be sustained, social cohesion must be maintained, structural integrity must hold, power must flow continuously. And every single one of these systems must function not for days or months, as they do on the International Space Station, but for decades or centuries, with no possibility of resupply. This is not a theoretical anxiety. We have hard data showing how difficult these systems are to maintain even in the best possible conditions. The International Space Station is humanity's most advanced long-duration habitat. It orbits just 400 kilometers above Earth's surface, well within the protective magnetic field of our planet, resupplied multiple times per year by cargo vehicles from several nations, staffed by crews that rotate every 6 months, and supported by thousands of engineers on the ground monitoring every system in real time. And it still breaks constantly. The ISS Environmental Control and Life Support System, known by its acronym ECLSS, is responsible for providing breathable air, drinkable water, comfortable temperature, and manageable humidity for the crew. It is the most critical set of systems on the station. And when engineers examined how much crew time the system actually consumed during the station's early years, the results were alarming. The maintenance burden was far larger than anyone had predicted, not because of exotic or unpredictable failures, but because of the ordinary grind of keeping complex mechanical and chemical systems running continuously in a hostile environment. Pumps wore out, filters clogged faster than expected, seals degraded in ways the models had not fully captured. The systems worked, but they demanded constant human attention, far more of it than the designers had budgeted for. The specific numbers shook mission planners and forced a fundamental reassessment of how much crew time any long-duration habitat must reserve for simply keeping itself alive. The ISS handles this burden because it has a supply chain. Spare parts arrive on cargo vehicles. Failed units get replaced with fresh hardware launched from Earth. Crews rotate before fatigue and confinement degrade their performance too severely. The station survives not because its systems are reliable enough to run without intervention, but because intervention is always available. An interstellar vessel would have none of these advantages. Every spare part must be carried on board or fabricated from raw material that is itself finite. Every failed component must be repaired by crew members who have been confined inside the same vessel for years, whose cognitive function may be degrading from radiation exposure, whose morale may be collapsing from isolation, and whose training may not cover the specific failure mode they are facing. There is no calling Houston for instructions when the communication delay is measured in years. There is no aborting the mission when the nearest safe harbour is decades of travel time behind you and decades more ahead. The maintenance burden that the ISS manages through a global logistics network must instead be managed by a small, isolated, increasingly fatigued crew operating entirely from internal reserves. And here is the fact that changes everything about how you should think about interstellar travel. The maintenance burden does not stay constant, it grows. Every mechanical system accumulates wear, every chemical process drifts from its optimal parameters. Every seal, every bearing, every filter, every circuit board has a finite operational lifetime, and those lifetimes are shortened by radiation exposure, thermal cycling, vibration, and the slow atomic scale degradation that affects all materials in space. As the mission continues, more components approach and exceed their design lifetimes. The rate of failure increases, the demand for spare parts accelerates, the crew spends more and more of their time keeping systems alive and less time on anything else. The ship does not cruise smoothly through the void, it deteriorates, and the deterioration accelerates. Consider what this means across the timescales involved. Even an optimistic interstellar mission to the nearest star system, Proxima Centauri at 4.24 light-years, would require approximately 85 years of travel at 5% of light speed. That is not a long airplane flight. That is longer than a human lifespan. The crew that departs Earth will not be the crew that arrives. Either the mission relies on multiple generations born and raised inside the vessel, or it relies on some form of suspended animation that does not currently exist and may not be biologically achievable for humans. Both approaches introduce profound new survival burdens on top of the engineering challenges. A generation ship must sustain a functioning society, not just a functioning machine. A hibernation vessel must keep unconscious human bodies alive and neurologically intact for decades, while the ship maintains itself with minimal or no active crew. None of this is to say that propulsion is easy. It is not. Accelerating even a modest payload to 5% of light speed requires energy outputs that dwarf anything humanity has ever produced. Current propulsion concepts, from nuclear pulse engines to laser-driven light sails to fusion drives, all face staggering engineering challenges. The breakthrough Starshot initiative, one of the most serious near-term interstellar proposals, envisions accelerating a gram-scale probe to 20% of light speed using a ground-based laser array. Even that stripped-down concept, carrying no crew, no life support, no return capability, faces unsolved problems in beam focusing, sail materials, and communication over interstellar distances. Scaling from a gram-scale probe to a crewed vessel multiplies the energy requirement by factors of billions. But the propulsion challenge, for all its enormity, has a clarity that the survival challenge lacks. You either generate enough thrust, or you do not. You either reach the target speed or you fall short. The success condition is binary and measurable. Survival has no such clarity. It is a continuous, open-ended, compounding struggle against entropy, degradation, and the biological limits of the organisms trapped inside the machine. There is no single moment where survival is achieved. There is only the next hour, the next day, the next year, each one demanding that every system continues to function within tolerances that grow tighter as reserves deplete and components age. The public imagination fixates on departure because departure is dramatic, a ship accelerating away from Earth, engines blazing, heading for the stars. That image is powerful, cinematic, and emotionally satisfying. It tells a story of courage and ambition, but the real story of an interstellar mission would not be the departure. It would be the 10,000th day, when the air recycler is running on its backup pump because the primary failed 6 months ago and the spare is showing early signs of the same fault. It would be the 20th year when the crew psychologist, if there is one, is documenting the third major interpersonal conflict that required physical separation of crew members in a habitat where physical separation means being 12 meters apart instead of 8. It would be the 50th year when the radiation shielding has absorbed so many particle impacts that its structural integrity is measurably reduced, and no one on board has the materials or the tools to reinforce it. This is what interstellar space does. It does not kill you with a single dramatic event. It grinds you down. It erodes your ship, your body, your mind, your supplies, and your margins, slowly, continuously, without pause for as long as you are inside it. And you are inside it for a very, very long time. Every interstellar mission concept that has ever been seriously proposed grapples with this reality in some form. Generation ships attempt to solve it by creating a self-sustaining society, but no closed ecological system has ever been maintained at stable equilibrium for more than a few years in any Earth-based experiment. Even Biosphere 2, the most ambitious and expensive attempt ever made on Earth's surface with every terrestrial advantage available, could not feed 8 people for 2 years without external intervention. Sleeper ships attempt to solve it by reducing the biological demand, putting most of the crew into some form of stasis, but this merely converts the biological survival problem into a mechanical reliability problem. The hibernation systems must function flawlessly for decades with no human oversight, and any failure during that time means death for the sleeper before anyone can intervene. Fast ships attempt to solve it by shortening the trip, but as previously noted, higher speeds increase radiation exposure and impact energy from the interstellar medium, creating new survival burdens that partially or fully offset the benefit of reduced travel time. There is no version of interstellar travel where the survival problem disappears. It can be redistributed, restructured, or reframed, but it cannot be eliminated. Because the survival problem is not a design flaw, it is a consequence of what interstellar space fundamentally is: an environment so vast, so empty, and so hostile that any closed system passing through it faces relentless pressure toward failure. The second law of thermodynamics guarantees that closed systems trend toward disorder. Life support systems, mechanical systems, biological systems, and social systems all obey this law. The only way to fight entropy is with energy and resources, and an interstellar vessel carries a finite supply of both. This is why the framing of interstellar travel must change. The question is not how do we get there? The question is how do we stay alive after we do? And the honest answer, based on everything we currently know about engineering, biology, and the physics of the interstellar medium, is that we do not yet know how. We have not solved long-duration closed-loop life support for a Mars mission lasting 2.5 years. We have not solved radiation shielding for deep space transit beyond low Earth orbit. We have not solved the psychological effects of prolonged isolation and confinement for durations beyond 1 year. And an interstellar mission demands all of these solutions simultaneously, at a level of reliability orders of magnitude beyond anything we have demonstrated, sustained for timescales orders of magnitude beyond anything we have attempted. The IS, for all its brilliance, is a machine that survives because Earth is 400 kilometers below it. An interstellar vessel would be a machine that must survive because nothing is anywhere near it. That difference is not a difference of degree. It is a difference of kind, and it is the difference that every interstellar travel discussion should start with but almost never does. This creates a problem that has no equivalent in any other form of exploration. Every previous human expedition into hostile territory, polar treks, deep ocean descents, orbital space flights, maintained a connection to a support base that could absorb the burden of failure. When something broke, help arrived. When supplies ran low, more were sent. When the crew reached their limits, they were brought home. These expeditions were hard, but they were open systems, drawing resources from the civilization that launched them for the duration of the mission. An interstellar vessel severs that connection permanently. It becomes a closed system the moment it passes beyond practical resupply range, and it must remain a closed system for the entirety of its transit. Nothing new enters, nothing broken gets replaced from outside. Every failure it will ever face must be resolved from within. The engineering consequences of this closure are severe, and they deserve precise detail. But the conceptual consequence is what matters here. The mission does not get easier as it progresses. It gets harder. Every day that passes draws down reserves that were fixed at departure, wears components closer to their breaking points, and brings the crew nearer to limits that can only shrink. The margin for error is widest on day one and narrowest on the last day, which is exactly the opposite of what the crew needs, because the last day is when the most degraded systems must perform their most critical functions. This inversion, where success buys you more time inside a worsening situation rather than an improving one, is the defining feature of interstellar survival, and the reason it is fundamentally harder than interstellar propulsion. The departure is the easy part. Not because it is actually easy, it is fantastically, almost impossibly hard, but it is the kind of hard that engineers understand. It has defined parameters, calculable energy requirements, and testable solutions. The survival problem is a different kind of hard. It is the kind of hard that accumulates, that compounds, that reveals new failure modes only after years of operation, and that punishes optimism with cascading breakdowns. The interstellar void does not care how elegant your launch was. It only cares how long your filters last. And your filters are not going to last long enough. Not yet. Not with anything we currently know how to build. To see how this plays out in practice, you only have to look at the only long-duration habitat humanity has ever operated, and watch how a ship begins to consume itself from the inside out, one failing system at a time. The International Space Station does not look like a machine that is constantly failing. From the outside, it is an engineering marvel, a gleaming lattice of solar arrays and pressurized modules orbiting Earth at 28,000 kilometers per hour. From the inside, the reality is different. The station is a repair shop that happens to be in space. Its crew members are mechanics first and scientists second, spending a staggering proportion of their working hours diagnosing faults, swapping components, tightening connections, cleaning filters, and coaxing aging hardware back to operational status. This is not a failure of design. It is the nature of what happens when complex systems operate continuously in a hostile environment. And every piece of data we have collected from the ISS tells us exactly what would happen to a vessel attempting the same feat across interstellar distances, except unimaginably worse. The environmental control and life support system aboard the station, the ECLSS, performs functions so fundamental that their absence means death within hours or days. It removes carbon dioxide from the cabin air. It generates oxygen through electrolysis of water. It recovers humidity from the atmosphere. It processes urine and wastewater back into drinkable water. It monitors trace contaminant levels and scrubs toxic gases before they accumulate to dangerous concentrations. It regulates cabin temperature and manages airflow between modules. Each of these functions depends on mechanical hardware, chemical processes, sensors, pumps, fans, valves, heaters, and control software working together continuously. The system never shuts down. It cannot be paused for maintenance without risking the crew's lives. A study analysing crew time records from the station's 4th through 8th increments, covering operations from late 2001 through early 2004, revealed a maintenance reality that shook mission planners. The actual crew time devoted to ECLSS maintenance exceeded the original design load estimates by approximately one order of magnitude. The designers had predicted that life support maintenance would require a modest, manageable slice of the crew's daily schedule. In practice, the station's environmental systems demanded roughly 3 to 3.3 hours of maintenance per day, from crews of 2 to 3 people. Over 35% of all maintenance time went specifically to air and waste handling subsystems. The largest contributor to this overrun was not exotic or unpredictable failure modes. It was ordinary mechanical wear, clogging, corrosion, and component drift, problems that any engineer would recognize from terrestrial systems, but that become far more consequential when the system in question is keeping human beings alive. The air revitalization system provides a concrete example. The carbon dioxide removal assembly on the American segment of the station uses a process called a 4-bed molecular sieve, which absorbs CO2 from cabin air onto zeolite pellets, then desorbs it by exposing the saturated bed to vacuum. This cycling process requires valves, heaters, and ducting that must operate thousands of times without failure. In practice, the valves experience seal degradation over time. Zeolite pellets generate dust that migrates into downstream components. The heaters develop uneven thermal profiles that reduce desorption efficiency. Each of these issues requires crew intervention, inspecting, cleaning, adjusting, or replacing components. The Russian segment uses a different approach aboard the Zvezda module, but faces its own maintenance demands. Neither system runs itself. Oxygen generation tells a similar story. The station's primary oxygen generation assembly uses electrolysis to split water molecules into hydrogen and oxygen gas. The oxygen goes into the cabin air supply. The hydrogen is either vented overboard or, when the Sabatier reactor is operational, combined with CO2 to produce water and methane, partially closing the loop. But the oxygen generation assembly has experienced repeated failures since its installation. Pump issues, cell stack degradation, and hydrogen sensor faults have forced the crew to fall back on backup systems, each with its own troubled maintenance history. Each time the primary system fails, the crew must troubleshoot, replace components, and restart the process, consuming hours of work and drawing from a finite inventory of spare parts. On the ISS, those spare parts arrive on the next cargo vehicle. On an interstellar ship, they do not arrive at all. Water recovery may be the most revealing system for understanding interstellar survival limits. The station's water recovery system processes two primary sources: humidity condensate collected from cabin air and pre-treated urine from the crew. The urine processor assembly uses a distillation process involving a centrifuge that separates water from waste products under low gravity conditions. This centrifuge has been one of the most failure-prone components on the entire station. During its initial activation, it failed almost immediately due to balance issues caused by how it was configured during installation. Subsequent years brought repeated centrifuge motor failures, brine blockages, and pre-treatment chemical supply issues, each demanding crew time and replacement hardware. When the water recovery system operates at full capacity with all upgrades installed, it now recovers approximately 98% of the water from urine and humidity. NASA achieved this milestone in 2023 by adding a brine processor assembly that extracts additional water from the concentrated waste brine that the original system discarded. 98% recovery is a remarkable engineering achievement. It is also, for interstellar purposes, still not enough. A 2% loss rate sounds negligible until you calculate what it means over decades. For every 100 litres of water entering the cycle, 98 litres come back and 2 litres are lost as residue, system inefficiency, or unrecoverable waste. On the ISS, those 2 litres are replaced by water delivered from Earth on cargo resupply missions. The station still receives multiple resupply vehicles per year carrying water and other consumables. Even at 98%, the loop does not close. It leaks, and the leak is filled from Earth. An interstellar vessel cannot receive resupply. That 2% loss must come from somewhere. Carry it all at departure, and you need to calculate the total water loss over the entire mission duration and bring enough surplus to cover it. A crew of 20 people requires roughly 240 litres of water per day for drinking, food preparation, and hygiene alone. But a closed-system vessel also cycles water through agricultural irrigation, humidity recovery, equipment cooling, and waste processing. The total water throughput through the recycling system could reach several hundred litres per day or more, depending on the food production architecture. At a 2% loss rate on even 300 litres of daily throughput, the ship hemorrhages 6 litres of unrecoverable water every single day. Over a 50-year transit, the cumulative deficit reaches over 100,000 litres, roughly 100 tonnes of water mass, that must be carried at departure on top of the operating supply. Increase the mission to 100 years, and the deficit doubles. The numbers are punishing even at humanity's best demonstrated recovery rate. But the problem is actually worse than simple arithmetic suggests. Recovery efficiency does not remain constant over time. It degrades. The distillation membranes that separate clean water from contaminants gradually foul with mineral deposits, biological films, and chemical residues. The catalytic oxidation systems that break down organic contaminants in recovered water slowly lose catalytic activity as their active surfaces become poisoned or physically eroded. Sensors that monitor water purity drift out of calibration. Pumps wear, seals age. Each of these degradation pathways reduces recovery efficiency incrementally, shifting the system from 98% toward 95, 92, 88. Every percentage point lost means more water vanishing from the closed loop with no way to replace it, and at the lower recovery rates, the daily deficit accelerates sharply. This degradation curve applies to every closed-loop system on the vessel, not just water. Air recycling, waste processing, food production if any is attempted, thermal regulation, all of them experience the same relentless drift toward lower efficiency. The physics behind this is inescapable. In any real physical process, some energy is lost to heat. Some matter is lost to inaccessible forms. Perfect recycling, 100% closure, is thermodynamically impossible. Every cycle through the loop loses something. Over enough cycles, those losses accumulate into a crisis. Engineers describe this phenomenon as the closure gap. It is the difference between the theoretical perfect recycling rate and the actual achievable rate under real operating conditions. On the ISS, the closure gap is filled by resupply. On a Mars-class mission lasting 2 to 3 years, the closure gap can be filled by carrying sufficient reserves, though even this requires careful mass budgeting. On an interstellar mission lasting decades or centuries, the closure gap becomes a death sentence unless it can be closed by some means other than carrying more consumables. There are only 2 theoretical options: either improve recycling efficiency to a level never achieved in any real system, or find a way to extract raw materials from the interstellar medium during transit. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter. Collecting useful quantities of hydrogen from this near-perfect vacuum at any plausible transit speed would require electromagnetic RAM, scoops of such enormous scale and energy consumption that they remain firmly in the domain of theoretical speculation, not engineering. This leaves the crew trapped inside a vessel whose life support systems are slowly leaking resources into unrecoverable forms. Water molecules break down and some hydrogen escapes through micro-leaks in the hull or is vented during chemical processing. Oxygen atoms bind to surfaces inside the air recycling system in forms that resist recovery. Nitrogen gradually migrates into biological waste products that the recycling system cannot fully process. Carbon accumulates in filter residues and solid waste. Each element drifts, molecule by molecule, from accessible to inaccessible, from useful to useless. The process is invisible on the scale of days or weeks. It is noticeable on the scale of months. It is critical on the scale of years. And it is catastrophic on the scale of decades. Now add the material degradation of the ship itself. Every structural component, every mechanical assembly, every electronic system, every seal and gasket and bearing on the vessel is subject to environmental assault from the moment the mission begins. In interstellar space, the primary agents of material degradation are galactic cosmic radiation, thermal cycling, mechanical vibration, and the slow chemical corrosion that occurs when metals and polymers interact with trace contaminants in the cabin atmosphere over long periods. Radiation damage to materials is cumulative and irreversible. When high-energy particles from galactic cosmic rays strike metallic structures, they displace atoms from their positions in the crystal lattice, creating defects called vacancies and interstitials. These defects accumulate over time, gradually changing the metal's mechanical properties. Ductile metals become brittle. Welds become stress points. Structural margins designed for the beginning of the mission erode year after year. This process, called radiation embrittlement, is well documented in nuclear reactor engineering, where reactor pressure vessels exposed to decades of neutron bombardment develop measurably reduced fracture toughness. An interstellar vessel would experience a comparable radiation flux, but for far longer durations, with no option to replace or anneal the affected structures. Polymers fare even worse. Radiation breaks the long molecular chains that give polymers their flexibility and strength. Seals made from elastomers harden and crack. Insulation becomes brittle and flakes away. Cable jackets degrade, exposing conductors to short circuits. Adhesives lose their bonding strength. Every polymer component on the ship has a radiation-limited lifetime, and that lifetime shrinks under the elevated galactic cosmic ray flux outside the heliosphere. NASA's Materials International Space Station experiment, known as MISSE, has tested hundreds of material samples in low Earth orbit, measuring degradation rates from atomic oxygen, ultraviolet exposure, and thermal cycling. Even in the relatively protected environment of low Earth orbit, polymer materials showed significant surface erosion and property changes within a few years. In the unshielded interstellar medium, the degradation would be substantially faster for radiation-sensitive materials. Electronics are another critical vulnerability. Modern spacecraft electronics rely on semiconductor devices that are sensitive to radiation-induced single-event effects, where a single energetic particle strikes a transistor and causes a bit flip, a latch-up, or permanent damage to the gate oxide layer. The ISS uses radiation-hardened electronics for critical systems and shielding for sensitive components, but even hardened devices have finite radiation tolerance limits. Over multi-decade interstellar transits, cumulative radiation dose would approach or exceed the tolerance of current radiation-hardened technology. The ship would need to either carry replacement electronics, which adds mass and itself degrades during storage, or develop radiation tolerance far beyond current capabilities. Compounding this, the semiconductor fabrication facilities needed to manufacture replacement chips are among the most complex and resource-intensive industrial systems on Earth. No interstellar vessel could carry a functioning chip fabrication facility, meaning every electronic component that fails must be replaced from a finite stockpile that was loaded at departure. Mechanical systems face their own slow destruction. Bearings, gears, actuators, and rotating assemblies all experience wear during operation. On Earth, worn components are replaced from manufacturing supply chains. In space, even aboard the ISS, critical rotating components like the station's control moment gyroscopes have required multiple replacements over the station's operational lifetime. These gyroscopes contain bearings that spin at thousands of revolutions per minute. Despite being designed for long life, bearing surface degradation eventually causes vibration, overheating, and failure. The station has experienced multiple gyroscope failures over its operational lifetime, requiring replacement with spares or complete unit swaps during spacewalks. An interstellar ship would rely on similar rotating mechanical systems for attitude control, centrifugal gravity generation if any is used, power conversion, and air and fluid circulation. Each rotating system would be subject to the same bearing wear, the same vibration-induced fatigue, and the same eventual failure. Without replacement bearings, the system stops. Without the system, some critical function ceases. Lubricants present a particularly insidious problem. Many spacecraft mechanisms rely on specialized lubricants to reduce friction and prevent wear. In the vacuum of space, conventional liquid lubricants evaporate rapidly, which is why spacecraft use either dry film lubricants like molybdenum disulfide or specially formulated low vapor pressure oils. Both types have finite operational lifetimes. Dry film lubricants wear away through mechanical contact. Low vapor pressure oils gradually evaporate even in vacuum, albeit slowly. Over decades of continuous operation, lubricated mechanisms experience increasing friction, increasing wear rates, and eventually seizure. Relubricating mechanisms in space requires specialized procedures and supplies that add to the ship's consumable mass budget. Now consider all of these degradation pathways operating simultaneously across thousands of individual components over decades of continuous operation inside a vessel that cannot pull into port for repairs. The mental model that most people carry of an interstellar ship is something like a submarine or an ocean liner, a sturdy vessel cruising through a passive medium. The accurate mental model is closer to a coral reef, a complex, fragile ecosystem of interdependent systems, each one slowly eroding, each one depending on the others to compensate for its weaknesses, and all of them trending toward failure at rates that increase with time. The maintenance burden this creates is not linear, it is exponential in character. In the early years of a mission, most components are new and operating within their design parameters. Failures are infrequent and manageable. Spare parts are plentiful, the crew has energy and time, but as the mission progresses, components begin reaching the end of their design lifetimes in overlapping waves. The rate of failure increases. The demand for spare parts grows. The crew spends more time repairing systems and less time on other essential tasks like food production, health monitoring, and navigation. The spare parts inventory depletes faster. Components that were designated as spares begin to show storage degradation from the same radiation and thermal environment that damaged the originals. The ship enters a phase where it is consuming its own reserves at an accelerating rate, like an animal burning body fat during a famine. The reserves buy time, but do not solve the underlying problem. Eventually they run out. NASA's reliability engineers quantified this dynamic in studies on ultra-reliable life support for long space missions. Their analysis concluded that achieving acceptable reliability for missions where resupply is impossible requires carrying spare components with a total mass approximately equal to the original system mass. That is, to achieve sufficient reliability for one life support system, you need to carry roughly two of them, one operating and one in reserve as parts. This mass doubling applies to every critical system on the vessel. Double the life support mass, double the power system mass, double the thermal control mass, double the navigation and communication mass, double the structural repair capacity. The ship's dry mass roughly doubles before it even accounts for propellant, crew provisions, or habitat volume. And the doubling assumes a mission duration on the order of years. For decades or centuries, the multiplier increases further because more failures are expected over longer operational periods. This is the mass spiral that makes interstellar mission architecture so punishing. Every kilogram of spare parts requires propulsion energy to accelerate. Every kilogram of propellant requires more propellant to carry it. Every additional kilogram of structure to house the spares requires more structure to support the mass. The rocket equation, which governs the relationship between payload mass, propellant mass, and achievable velocity, is exponential and merciless. Small increases in payload mass produce large increases in required propellant. For interstellar velocities, these exponential penalties are devastating. A ship that needs to carry double its dry mass in spares must carry exponentially more propellant, which in turn requires a larger engine, stronger structure, and more thermal management, all of which need their own spares. The vehicle spirals toward masses so large that no conceivable propulsion system can accelerate them to useful interstellar speeds. Some mission architects have proposed in-situ manufacturing as a solution, equipping the ship with fabrication tools that can produce replacement parts from raw feedstock during transit. This is technically plausible for simple components like structural brackets, tubing, and basic mechanical parts. Three-dimensional printing using metal and polymer feedstock could theoretically produce replacements for a subset of failed components, but fabrication requires energy, raw materials, and equipment that itself degrades and requires maintenance. The printer's laser or electron beam source has a finite operational lifetime. The feedstock supply is finite. The precision achievable by onboard fabrication may be insufficient for critical components like pressure vessel walls, high-speed bearings, or electronic circuit boards. And the range of materials available is limited to whatever feedstock was loaded at departure. You cannot three-dimensionally print a new semiconductor chip, a new catalytic converter substrate, or a new cryogenic seal material from generic metal powder. There is another system whose failure would kill the crew before any seal cracks or any pump seizes, and it receives almost no attention in public discussions of interstellar travel. Food. Every human being on the vessel must consume roughly 2,000 calories per day, every day, for the duration of the mission. For a crew of 20 over a 50-year transit, the total caloric requirement reaches hundreds of millions of calories, translating to hundreds of tons of stored food mass that must be accelerated to interstellar velocity at departure and that degrades in storage as nutritional content breaks down over years and decades. Vitamins oxidize, fats go rancid, proteins denature. Caloric content may remain stable in sealed packaging for a time, but micronutrient quality declines steadily. A crew surviving on stored rations for decades would face progressive nutritional deficiencies even if the rations remained technically edible. And those deficiencies would compound the immune suppression, bone loss, and cognitive decline already being driven by radiation and confinement. The alternative is growing food on board. This sounds straightforward and is, in practice, one of the most fragile and failure-prone systems ever attempted in a closed environment. Growing crops requires light, water, nutrients, atmospheric control, pollination, pest management, and soil or hydroponic media, all maintained at biological tolerances far more demanding than those of mechanical systems. A pump can tolerate a 5% variation in flow rate and still function. A crop of wheat cannot tolerate a 5% variation in atmospheric CO2, concentration without measurable yield loss. The biological tolerances are tighter, the failure modes are less predictable, and the consequences of failure are caloric deficit, which, unlike a mechanical breakdown, cannot be repaired. Lost calories are simply gone. Biosphere. 2 demonstrated exactly how difficult closed agricultural systems are to maintain. Within 2 years of sealing, the facility experienced plummeting oxygen levels, CO2 spikes that stressed both plants and inhabitants, crop-damaging ant and cockroach population explosions, the extinction of nearly all pollinating insect species inside the enclosure, and fungal infestations that attacked the food crops. The facility was designed by experienced ecologists with a budget of over $150 million and sat on the surface of Earth, where gravity, sunlight, and external intervention were all available. It still failed. The inhabitants lost weight. Nutritional deficiencies appeared. The agricultural system could not sustain the caloric needs of 8 people for 2 years in ideal terrestrial conditions. An interstellar vessel would attempt the same feat under conditions that are worse in every measurable dimension. The lighting must be artificial, requiring continuous electrical power. The water must come from the ship's own recycling loop, carrying whatever trace contaminants the recovery system fails to remove, contaminants whose effects on plant growth over years of accumulation are poorly understood. The nutrient supply must be recycled from human waste and crop residues, a composting process that works on Earth because of a diverse soil microbiome that has co-evolved with terrestrial plants over hundreds of millions of years. Replicating that microbiome inside a sealed vessel and maintaining it at functional diversity across decades is a problem that soil science has not solved and may not be close to solving. Soil microbiomes are among the most complex ecosystems on Earth, containing thousands of interacting species of bacteria, fungi, and microorganisms. Simplify that ecosystem, as any closed vessel inevitably would, and nutrient cycling becomes less efficient, less predictable, and more prone to sudden collapse. Crop disease presents a particularly dangerous threat. On Earth, agricultural disease is managed through crop rotation across different fields, genetic diversity across thousands of cultivars, chemical treatments manufactured by a global industrial base, and the option of importing food from unaffected regions if a local crop fails. An interstellar vessel has none of these options. Its agricultural area is fixed and cannot be expanded. Its genetic stock is limited to whatever seeds or tissue cultures were loaded at departure. Its chemical treatment options are limited to whatever was brought aboard. And if a fungal blight or bacterial infection sweeps through the growing chambers, there is no external food source to fall back on. The crew eats stored reserves until the growing system recovers, if it recovers, and every day of stored rations consumed is a day subtracted from the finite emergency supply. The caloric deficit problem compounds over time in exactly the same way as the water deficit and the spare parts deficit. Small agricultural shortfalls in one growing cycle mean slightly less seed stock for the next cycle, slightly less biomass for composting, slightly less nutritional diversity for the crew. The shortfall propagates forward, growing incrementally worse with each cycle, until the crew is chronically undernourished, weaker, more susceptible to illness, less cognitively sharp, and less able to perform the maintenance tasks that every other system on the ship demands of them. Food production failure does not kill quickly, it kills slowly by degrading everything else. Now consider the system that every other system depends on: power. Every function described in this video, air recycling, water recovery, food production lighting, thermal regulation, radiation shielding if active magnetic systems are used, electronic systems, communication, navigation, and the fabrication tools that represent the crew's last resort repair capability requires continuous electrical power. If the power system fails, everything fails. If the power system degrades, everything degrades. Power is the upstream dependency that sits above every other survival system in the hierarchy, and it has its own finite lifespan. An interstellar vessel has limited options for power generation. Solar panels become useless within the first few astronomical units of departure, as the inverse square law reduces solar flux to negligible levels far from any star. Chemical fuel cells carry insufficient energy density for multi-decade missions. The only realistic power sources for interstellar transit are nuclear, either fission reactors or radioisotope thermoelectric generators, known as RTGs. RTGs generate electricity from the heat produced by radioactive decay of isotopes like plutonium-238. They are proven technology, powering spacecraft like the Voyager probes for decades. But their output is modest, on the order of hundreds of watts, and it declines continuously as the isotope decays. Plutonium-238 has a half-life of roughly 87 years, meaning that after 87 years, an RTG produces only half its original power. For an interstellar vessel requiring kilowatts or megawatts of continuous power to sustain life support, agriculture, and maintenance systems, RTGs are insufficient. They can supplement but cannot serve as the primary power source. Fission reactors offer higher output but introduce their own survival burdens. Reactor fuel, typically enriched uranium-235, is consumed during operation. A reactor sized to power a crewed vessel for decades must carry enough fuel for the entire mission, and that fuel mass adds to the propulsion burden. The reactor's control systems, coolant loops, heat exchangers, and shielding all require maintenance. Reactor shielding materials are subject to the same neutron embrittlement that affects structural materials under galactic cosmic ray bombardment, but at far higher flux levels because the reactor itself is a neutron source. The combination of external cosmic radiation and internal reactor radiation creates a dual degradation pathway for the materials closest to the reactor, accelerating embrittlement beyond what either source would cause alone. Reactor coolant systems rely on pumps, valves, and heat exchangers that are among the most maintenance-intensive components in any nuclear installation. On Earth, nuclear power plants employ hundreds of specialized technicians and receive replacement components from global manufacturing supply chains. An interstellar vessel must manage reactor maintenance with a small crew using only the tools and parts on board. A coolant leak in a terrestrial reactor triggers an emergency response from external teams with external resources. A coolant leak aboard an interstellar vessel triggers an emergency response from the same fatigued, radiation-exposed crew that is already behind on maintenance for every other system. And if the reactor must be shut down for repairs, every system on the ship loses power simultaneously. Life support switches to battery reserves that last hours, not days. Food production lights go dark. Thermal regulation ceases. The habitat begins cooling toward the ambient temperature of interstellar space. The crew works against a hard deadline to restore reactor function before the batteries die and the air stops cycling. This scenario is not hypothetical. It is the predictable consequence of operating a complex nuclear system for decades without access to an industrial support base. Reactor incidents will occur. The only question is whether the crew can resolve them before the cascading loss of power becomes irreversible. Power degradation does not announce itself dramatically. Like every other system on the vessel, it manifests as a slow decline. Reactor output drops fractionally as fuel is consumed. Conversion efficiency decreases as thermoelectric or turbine components wear. Power distribution systems accumulate resistance as connectors corrode and insulation degrades. The ship's total available power budget shrinks year by year, and every system that depends on that power must either reduce its consumption or accept lower performance. Less power for lighting means lower crop yields. Less power for water recycling means lower recovery rates. Less power for air processing means slower CO2 removal. The power decline propagates through every system it feeds, amplifying every other degradation pathway simultaneously. It is the quiet multiplier that makes everything else worse. The ship, in essence, is a closed industrial civilization that must maintain itself with a fixed inventory of raw materials, tools, and knowledge, operating in an environment that actively degrades everything inside it. No civilization in human history has ever operated under such constraints. Even the most isolated communities on Earth, Antarctic research stations, submarine crews, remote island populations, have always had access to resupply, external resources, or the option of abandoning their position and returning to a larger support network. An interstellar vessel has none of these. It must be entirely self-sufficient in a way that nothing humans have ever built has achieved. The most uncomfortable implication of all of this is that the ship does not need to suffer a catastrophic failure to die. It does not need a meteor strike, a reactor meltdown, or a hull breach. It just needs time. Given enough time, the ordinary, predictable, well-understood processes of material degradation, component wear, and efficiency loss will grind the vessel's systems below the threshold of habitability. The ship eats itself, not through some dramatic act of destruction, but through the patient, relentless accumulation of 10,000 small failures, each one individually manageable, collectively fatal. The ISS has operated for roughly 25 years. During that time, it has required continuous resupply, multiple module replacements, hundreds of spacewalks for external repairs, and constant ground support to remain habitable. It has experienced air leaks, coolant leaks, computer failures, gyroscope failures, toilet failures, power distribution faults, and countless smaller anomalies. Each one was resolved because Earth was nearby. Multiply the station's operational lifetime by a factor of 4 to match a 100-year interstellar transit. Remove all resupply, remove all ground support, remove the option of evacuation, and add the elevated radiation environment of interstellar space. The resulting scenario is not speculative. It is the direct, documented, mathematically predictable consequence of operating complex systems in isolation over timescales that exceed their design lifetimes. This is what it means for the ship to eat itself. Not a metaphor, a physical process. The vessel consumes its spare parts, its consumable reserves, its structural margins, and its operational buffers at a rate that increases with every year of operation. The crew watches the margins shrink. They patch what they can. They improvise when the manuals do not cover the failure mode. They cannibalize non-essential systems to keep essential ones running. They accept reduced performance in one area to maintain bare minimum function in another. And through all of this, the ship continues to age, the radiation continues to accumulate, and the next failure is always closer than the last one. But the ship is not the only thing breaking down. The human beings inside it are subject to an entirely different set of degradation processes, ones that no amount of spare parts can fix, ones that strike at the crew's ability to think, to decide, to cooperate, and to maintain the very systems on which their survival depends. The machine and its operators are failing at the same time. The ship is degrading. Every seal, every pump, every filter trending toward failure across decades of unbroken operation. But there is something inside the ship that degrades faster than any mechanical component and is infinitely harder to replace. The crew, the human beings tasked with maintaining the vessel, operating its systems, making decisions under stress, and holding together a functional social structure for the duration of the mission, are themselves biological machines. And biological machines are breathtakingly fragile when exposed to the conditions of interstellar space. This is the part of interstellar travel that receives the least public attention and poses the greatest unsolved threat. Propulsion captures the imagination. Engineering reliability generates technical papers. But the slow, cumulative destruction of the human body and mind by radiation, confinement, isolation, and the absence of every environmental condition that human biology evolved to depend on represents a category of problem that no amount of engineering can fully solve. Because you cannot carry spare human beings. You cannot swap out a damaged brain the way you swap out a failed pump. The crew you launch with is the crew you have for the entire mission, and everything about interstellar space conspires to make them less capable, less healthy, and less psychologically stable with every passing year. Start with radiation, not as an abstract hazard, but as a specific, documented, physically measured assault on human tissue. Outside the protective magnetic bubble of the heliosphere, the dominant radiation threat comes from galactic cosmic rays. These are not the relatively low-energy particles that astronauts encounter in low Earth orbit, where the planet's magnetic field deflects the most dangerous components. The galactic cosmic rays described earlier are dangerous to materials and electronics, but their effect on living tissue is far more insidious. The heavy ions that make up the most damaging component of this radiation, particularly iron nuclei carrying energies exceeding 1,000 mega-electron volts per nucleon, interact with biological matter in ways that no other common radiation source replicates. When such a particle strikes living tissue, it does not merely ionize a few molecules. It cuts a track of destruction through every cell in its path, shattering DNA strands, obliterating cellular structures, and triggering cascades of secondary radiation as the particle fragments and scatters energy into surrounding tissue. The biological damage from heavy ion exposure is qualitatively different from the damage caused by lower energy radiation like X-rays or gamma rays. Lower energy radiation tends to cause scattered, repairable DNA damage, single-strand breaks that the cell's repair machinery can often fix. Heavy ions cause clustered damage, multiple simultaneous breaks in both strands of the DNA helix, along with destruction of the surrounding repair proteins. These complex lesions are far more difficult for cells to repair correctly. When repair fails, the result is either cell death or, worse, a cell that survives with corrupted genetic instructions, potentially leading to cancer, tissue dysfunction, or premature aging of the affected organ. The cancer risk alone is significant. NASA has established career radiation exposure limits for astronauts based on an acceptable level of excess cancer mortality risk. For missions in low Earth orbit, these limits are manageable because exposure rates are relatively low and mission durations are measured in months. A 6-month stay on the ISS typically results in a cumulative dose of roughly 80 to 160 millisieverts, depending on solar activity. Annual exposure in interstellar space outside the heliosphere is estimated at approximately 400 to 600 millisieverts from galactic cosmic rays alone, roughly 3 to 4 times the annual dose aboard the station. Over a decade of interstellar transit, cumulative exposure would reach 4 to 6 sieverts, a dose that substantially increases lifetime cancer risk and begins approaching thresholds associated with acute radiation syndrome if delivered in shorter bursts during solar particle events. But cancer is a long-term risk. The more immediately mission-critical danger is what galactic cosmic radiation does to the brain. Over the past decade, a body of research funded by NASA and conducted at facilities including the NASA Space Radiation Laboratory at Brookhaven National Laboratory has produced findings that should alarm anyone seriously contemplating crewed interstellar missions. Researchers led by Charles Lemoli at UC Irvine and others have subjected rodents to charged particle radiation at doses and energies representative of the galactic cosmic ray environment. The results have been consistent and disturbing across multiple independent studies. Exposure to space-relevant doses of heavy ion radiation caused significant and persistent cognitive impairment in rodents. Animals showed measurable deficits in spatial memory, the ability to navigate physical environments. They showed impaired episodic memory and degraded recognition memory. They showed reduced executive function, the higher-order cognitive processes responsible for planning, decision-making, and behavioral flexibility. And they showed altered fear extinction, meaning their ability to learn that a previously threatening stimulus was no longer dangerous was compromised, leaving them in a state of elevated and persistent anxiety. The neural basis of these deficits was visible under microscopic examination. Irradiated animals showed significant reductions in dendritic complexity in the medial prefrontal cortex, a brain region critical for decision-making and impulse control. Dendrites are the branching extensions of neurons that receive signals from other cells. When dendritic complexity is reduced, the neuron's ability to integrate information from multiple sources is degraded. The irradiated animals also showed reduced spine density along those dendrites. Dendritic spines are the tiny protrusions where synaptic connections form. Fewer spines mean fewer functional connections between neurons. The brain's communication network was physically eroded by the radiation exposure. Additionally, researchers observed persistent neuroinflammation in irradiated brains. Microglial cells, the brain's resident immune cells, became chronically activated, releasing inflammatory molecules that further damaged surrounding neurons. This inflammation did not resolve after the radiation exposure ended. It persisted for months in the animal studies, and separate research on lifelong effects found that a single exposure to heavy ion radiation in young adulthood produced measurable changes in brain structure and cognitive function that lasted the animal's entire remaining lifespan. The damage was not temporary, it was permanent. These findings carry a specific and terrifying implication for interstellar missions. The crew would be exposed to galactic cosmic rays continuously for the entire duration of transit. There is no period of non-exposure. There is no recovery interval. The radiation damage to their neural tissue would accumulate day after day, year after year, progressively degrading the cognitive functions most essential to mission success. Memory, spatial reasoning, decision-making, problem-solving, emotional regulation, and the ability to learn new information and adapt to novel situations. The very faculties the crew needs to maintain the ship, diagnose failures, improvise repairs, and manage interpersonal conflicts would be the faculties most damaged by the environment they are traveling through. Shielding against galactic cosmic rays is the obvious response, and it is far harder than most people assume. Lower energy radiation, like solar particle events that consist mostly of protons, can be effectively blocked by moderate amounts of material. A shelter lined with polyethylene or water, equivalent to a few centimeters of dense shielding, can reduce solar particle exposure significantly. Galactic cosmic rays are a different beast entirely. Their energies are so high that they penetrate conventional shielding materials with relative ease. Worse, when heavy ions strike dense shielding materials like metals, they fragment and produce showers of secondary particles, neutrons, protons, and lighter ions that can be more biologically damaging than the original particle. This phenomenon, called secondary radiation production, means that simply piling on more shielding mass can actually increase the dose to the crew rather than decrease it if the wrong materials are used. Effective shielding against galactic cosmic rays requires either enormous thickness of low-density hydrogen-rich material on the order of several meters of water or polyethylene surrounding the entire pressurized habitat, or active magnetic shielding, using superconducting coils to deflect charged particles before they reach the hull. Both approaches carry crippling mass penalties. Several meters of water shielding around a habitat module would add thousands of tons to the vessel's mass, feeding directly into the propulsion mass spiral described earlier. Active magnetic shielding requires superconducting magnets, cryogenic cooling, and enormous energy input, all adding mass, complexity, and maintenance burden. No practical, flight-ready galactic cosmic ray shielding system exists today. The problem is not merely unsolved, it is not close to solved. Current research is focused on understanding the biological effects well enough to set meaningful exposure limits, not on deploying effective countermeasures. This means that any crewed interstellar mission launched with foreseeable technology would expose its crew to continuous galactic cosmic radiation with only partial shielding at best. The cognitive degradation observed in laboratory animals would, to some degree, occur in the crew. The question is not whether, but how much and how fast. And the honest answer, based on current evidence, is that the crew's cognitive capacity would measurably decline over the course of a multi-decade transit, leaving them progressively less capable of performing the complex tasks required to keep themselves alive. Now layer the psychological dimension on top of the biological one. Radiation degrades the brain's hardware. Isolation and confinement degrade its software. The psychological effects of long-duration confinement have been studied extensively in analog environments, simulations designed to replicate as closely as possible the conditions of extended space missions without actually leaving Earth. The most famous of these is the Mars 500 experiment, conducted in Moscow between 2010 and 2011, in which 6 volunteers were sealed inside a simulated spacecraft for 520 days, the approximate duration of a round-trip Mars mission including surface stay. The psychological data from Mars 500 and similar analog studies, including the HISEAS missions in Hawaii and Antarctic winter-over expeditions paint a consistent picture. Confinement produces a predictable sequence of psychological changes over time. The initial phase is characterized by elevated alertness and engagement as participants adapt to their new environment. This phase gives way to a prolonged period of deprivation effects as the monotony, restriction, and isolation of the environment take hold. Dopamine and serotonin levels, the neurochemicals most associated with motivation, pleasure, and emotional stability, decline measurably over the course of long confinement. Depression symptoms increase in a roughly linear fashion with mission duration. Sleep quality deteriorates. Circadian rhythms drift. Social participation decreases. Interpersonal conflicts increase in frequency and intensity. The most critical finding for interstellar mission planning is that adverse psychological conditions become most likely after the halfway point of a mission. In the HIS-EAS analog studies lasting 8 to 12 months, the period of greatest psychological instability began at approximately 6 months. Crew members experienced increased volatility, mood disruptions, changes in activity levels, and breakdowns in team cohesion during the second half of the simulation. This pattern is consistent with earlier observations from submarine deployments and Antarctic expeditions, where a phenomenon sometimes called the third quarter effect describes a period of heightened psychological distress, roughly 3/4 of the way through a confined deployment. Now apply this finding to an interstellar mission. A transit lasting 85 years to the nearest star has no meaningful halfway point that the human mind can grasp. The crew does not have the psychological anchor of a visible countdown to arrival. They cannot see their destination growing closer in any perceptible way. They cannot see Earth receding meaningfully in the opposite direction, because Earth disappeared from naked eye visibility within the first months of the journey. They are suspended in a void that looks identical in every direction, with no external reference point to mark progress, no seasonal variation, no change in the environment, nothing but the interior of the vessel and the faces of the same small group of people, day after day, year after year, decade after decade. The psychological architecture that humans rely on to endure hardship depends heavily on temporal framing. The belief that the hardship will end, that relief is approaching, that patience will be rewarded. Prisoners endure sentences because release dates exist. Soldiers endure deployments because rotation schedules exist. Even Antarctic winter-over crews endure their isolation because the supply plane returns in spring. An interstellar crew has no such anchor. For the first generation aboard a generation ship, the destination is not a place they will ever see. They will live their entire lives inside the vessel and die before arrival. Their children may face the same reality. The psychological toll of knowing that you are imprisoned inside a machine for the rest of your natural life, that you will never breathe unrecycled air, never feel wind, never see an open sky, never walk more than a few hundred meters in any direction, is not something that any analog study has been able to replicate, because no analog study has ever lasted longer than about 520 days, and all participants knew that the simulation had an end date. The interaction between radiation-induced cognitive damage and confinement-induced psychological deterioration creates a feedback loop that may be the single most dangerous threat to an interstellar mission. Consider what happens when both processes operate simultaneously over years. Radiation gradually impairs the crew's executive function, their ability to plan, prioritize, and make sound decisions under pressure. Confinement gradually erodes their emotional resilience, their motivation, and their capacity for cooperative behavior. As executive function declines, crew members become more prone to errors in maintenance tasks, less able to troubleshoot novel failure modes, and less effective at managing interpersonal conflicts rationally. As emotional resilience erodes, those interpersonal conflicts intensify and become harder to resolve, increasing stress levels that further impair cognitive performance. This is not speculation. It is the documented interaction between cognitive impairment and psychological stress in every clinical setting where both have been studied. Patients with even mild cognitive deficits show amplified responses to psychosocial stressors. Individuals under chronic psychological stress show accelerated cognitive decline. The two processes potentiate each other. On an interstellar vessel, Both processes are being driven continuously by environmental conditions that cannot be altered or escaped. The crew cannot take a vacation from the radiation. They cannot take a break from the confinement. They cannot rotate to a fresh crew. They are locked inside the feedback loop for the duration of the mission, and the loop tightens with every passing year. The physical health consequences extend beyond the brain. Prolonged exposure to the space environment, even in the partial protection of low Earth orbit, produces documented changes across nearly every organ system in the human body. Bone density decreases at a rate of approximately 1 to 2% per month in microgravity, a condition that can be partially mitigated by exercise but not fully prevented. If the interstellar vessel does not provide artificial gravity through rotation, the crew faces progressive skeletal weakening that increases fracture risk and limits physical capacity. Muscle mass declines alongside bone density. Cardiovascular function adapts to the reduced gravitational load, resulting in cardiac atrophy, reduced blood volume, and orthostatic intolerance. The immune system undergoes changes that are still being characterized but appear to include both dysregulation, inappropriate immune activation leading to inflammation, and suppression, reduced ability to fight infections. Radiation compounds every one of these effects. Galactic cosmic rays damage the cardiovascular endothelium, the lining of blood vessels, contributing to accelerated atherosclerosis. They suppress immune function through direct damage to lymphocytes and bone marrow. They increase the rate of cataract formation by damaging the lens of the eye. They impair wound healing by damaging the rapidly dividing cells responsible for tissue repair. A crew member who suffers a fracture due to radiation-weakened bone must then rely on radiation-impaired healing processes to recover, attended by crew members whose decision-making capacity has been degraded by the same radiation. Every medical emergency becomes harder to manage because the radiation that caused or worsened the emergency has simultaneously degraded the crew's ability to respond to it. There is a dimension of biological damage that extends beyond the individual crew member and reaches into the mission's future: reproductive harm. If the mission spans multiple generations, the crew must reproduce successfully aboard the vessel. Galactic cosmic radiation makes this far more dangerous than reproduction on Earth. Heavy ion exposure damages not only the somatic cells of the body, the cells that make up organs and tissues, but also the germ cells, the eggs and sperm that carry genetic information to the next generation. DNA damage in germ cells does not merely harm the individual who receives the dose. It introduces mutations into the genetic lineage that are passed to all subsequent descendants. On Earth, each child is born with approximately 60 to 80 new mutations not found in either parent's genome, a baseline rate that increases by roughly 1 to 2 additional mutations per year of the father's age at conception. In large populations, natural selection filters out the most harmful of these mutations over many generations, keeping the overall genetic burden manageable. Galactic cosmic radiation would increase this mutation rate substantially. Heavy ions cause the same clustered, complex DNA damage in germ cells that they cause in neurons, damage that cellular repair mechanisms handle poorly. The result is an elevated rate of de novo mutations in every child conceived aboard the vessel. Some of these mutations will be neutral, some will be mildly harmful, a small percentage will be severely harmful, causing developmental abnormalities, organ dysfunction, or conditions incompatible with life. In a large population, harmful mutations are diluted across a vast gene pool and gradually removed by natural selection. An interstellar vessel does not carry a large population. Proposed generation ship crews range from a few hundred to a few thousand individuals, far below the effective population sizes that geneticists consider necessary for long-term genetic health. In small populations, harmful mutations accumulate through a process called genetic drift, where random chance rather than fitness determines which alleles survive into the next generation. This process, called mutational meltdown in its extreme form, has been documented in small isolated populations of animals and plants on Earth. It leads to progressive decline in average fitness across generations, as the burden of harmful mutations grows faster than selection can remove them. Now combine genetic drift with an elevated mutation rate from continuous radiation exposure. Each generation aboard the vessel starts with a slightly higher load of harmful mutations than the one before. Fertility may decline as reproductive cell damage accumulates. Miscarriage rates may increase. the proportion of children born with congenital conditions rises. The effective working population, the number of healthy adults capable of maintaining the ship, shrinks with each generation. The vessel requires a minimum number of competent maintainers to function. If the genetically healthy fraction of each new generation falls below that minimum, the ship loses the ability to sustain itself, not through any mechanical failure, but through the biological degradation of the population that operates it. This genetic burden is invisible in the first generation, it becomes detectable in the second, it becomes critical by the third or fourth, and it is essentially irreversible without genetic engineering capabilities that are currently theoretical for humans. The generation ship does not merely need to sustain life, it needs to sustain genetically healthy life across a small, isolated, continuously irradiated population for centuries. No experiment in human history has tested whether this is possible. The genetic evidence from small, isolated human populations on Earth, communities that experienced elevated rates of genetic disease and reduced fitness over centuries, suggests that it may not be. Even without the additional mutational burden of galactic cosmic radiation, the crew also faces a biological threat that is not about their own cells, but about the trillions of microbial cells living inside and around them. The human microbiome, the community of bacteria, fungi, and other microorganisms that inhabits the gut, skin, respiratory tract, and other body surfaces, is essential to health. It aids digestion, produces vitamins, trains the immune system, and competes with pathogenic organisms for resources. On Earth, the human microbiome is continuously refreshed and stabilized by contact with the environment: soil, water, food, other people, animals, and the vast microbial diversity of the planetary biosphere. Inside an interstellar vessel, that environmental reservoir vanishes. The crew carries their microbiomes aboard at departure, but those microbial communities immediately begin drifting. Without the stabilizing input of a diverse external environment, the microbial ecosystem inside the ship simplifies. Species that are well adapted to the artificial environment of the habitat proliferate. Species that depend on ecological niches that do not exist aboard the ship decline and eventually disappear. The diversity of the microbial community decreases over time, and lower diversity is consistently associated with increased susceptibility to infection, inflammatory bowel conditions, immune dysregulation, and metabolic disorders. This microbial drift has already been observed aboard the ISS. Studies of the station's microbial environment have found that the station harbours a distinct and less diverse microbial community than terrestrial environments, with elevated proportions of stress-resistant and antibiotic-resistant organisms. The sealed, recirculated air environment of the station selects for microbes that thrive under those specific conditions, which are not necessarily the microbes that are beneficial to human health. Over the 25 years of station operation, the microbial profile has shifted measurably, and crew members have reported increased incidents of skin irritation, respiratory sensitivity, and minor infections compared to terrestrial baselines. Scale this drift to interstellar timescales and the implications grow severe. Over decades, the ship's microbial ecosystem would become increasingly dominated by a small number of highly adapted species. Some of those species may be opportunistic pathogens that, in the absence of competition from a diverse microbial community, colonize surfaces and human bodies more aggressively. Antibiotic resistance, already a growing problem on the ISS, would compound over years of selective pressure inside a closed environment where every antibiotic used exerts selection on the entire habitat's microbial population simultaneously. The crew's immune systems, already suppressed by radiation exposure, would face an increasingly hostile microbial environment with a progressively narrower pharmaceutical arsenal to fight it. The microbiome problem links directly to the food production problem described earlier. The crops growing in the ship's agricultural chambers depend on their own microbial communities for nutrient uptake, disease resistance, and soil health. If the ship's microbial ecosystem drifts toward a simplified, pathogen-enriched state, the agricultural microbiome suffers alongside the human one. Crop diseases become more likely. Soil nutrient cycling becomes less efficient. The food system and the human health system degrade together, driven by the same underlying microbial simplification, which itself is an unavoidable consequence of operating a sealed biological community without the stabilizing influence of a planetary biosphere. The cumulative medical burden over decades of transit would be extraordinary. Even with the best conceivable onboard medical facilities, the crew would face a rising tide of chronic conditions: cancer, cardiovascular disease, cataracts, osteoporosis, immunodeficiency, and neurodegenerative symptoms resembling early-onset dementia. The onboard pharmacy would need to cover a spectrum of medications that itself degrades over time, since most pharmaceutical compounds have shelf lives measured in months to a few years, not decades. Storing medications for a century-long voyage would require either massive overstock to account for degradation, active pharmaceutical manufacturing capability on board, or the acceptance that many medical conditions will become untreatable as the mission progresses. Surgery presents another stark limitation. If a crew member develops appendicitis, a kidney stone requiring intervention, or a traumatic injury from an equipment malfunction, the mission must rely on whoever aboard has surgical training to perform the procedure in a microgravity or artificial gravity environment, with limited equipment, limited anesthesia supplies, and no ability to call for consultation in real time. Surgical capability in space remains rudimentary. Experiments have been conducted on performing basic procedures in simulated microgravity, but nothing approaching the range of surgical interventions available in a terrestrial hospital has been demonstrated in space. Over a multi-decade mission, the statistical probability of a crew member requiring surgical intervention that exceeds the ship's medical capability approaches certainty. At that point, the crew faces a choice between attempting an inadequate procedure or watching a crew member suffer and potentially die from a treatable condition. The social structure of the crew faces its own form of erosion. Human social groups in confined, isolated environments develop predictable dysfunctions over time. Cliques form, power dynamics shift, resentments accumulate, communication patterns degrade. The initial cooperative spirit of a shared mission gives way, gradually and often invisibly, to territorial behavior, social withdrawal, and chronic low-grade conflict. These dynamics have been observed in every long-duration isolation study ever conducted, from submarine deployments to Antarctic stations to the Mars 500 simulation. They are not failures of character or selection. They are emergent properties of human psychology under confinement. On an interstellar vessel, these social dynamics interact with the cognitive and emotional degradation already described. A crew member whose executive function has been impaired by radiation is less able to regulate their emotional responses during a conflict. A crew member whose serotonin levels have been depleted by chronic confinement is more likely to interpret neutral social interactions as hostile. A crew member whose sleep quality has deteriorated over years of circadian disruption is more irritable, less empathetic, and less capable of the sustained diplomatic effort required to maintain functional relationships in an inescapable social environment. The social fabric of the crew thins under the same forces that thin the ship's structural margins, and for the same fundamental reason. Closed systems degrade under sustained stress, whether those systems are mechanical or human. The deepest cruelty of this degradation is its timing. The crew's biological and psychological decline does not occur in isolation from the ship's engineering decline. Both processes accelerate in parallel. As the vessel ages and maintenance demands increase, the crew is called upon to perform more complex and more frequent repair tasks at precisely the time when their cognitive capacity to perform those tasks is diminishing. A repair procedure that a fresh, well-rested, cognitively sharp crew member could complete in 2 hours might take a fatigued, radiation-impaired, psychologically depleted crew member 4 hours with a higher probability of error. Errors in maintenance create secondary failures. Secondary failures demand additional repair time. The crew falls further behind the maintenance curve and the ship's condition deteriorates faster. This convergence of human and mechanical degradation is the mechanism by which an interstellar mission transitions from struggling to dying. It is not a single point of failure. It is a broad systemic erosion of capacity on every front simultaneously. The ship needs more from the crew at the exact moment the crew has less to give. The crew needs more from the ship's medical and life support systems At the exact moment those systems are struggling to maintain baseline function, both the machine and the people inside it are being ground down by the same environment at the same time, and neither can compensate for the other's decline because both are declining together. No crude interstellar concept has proposed a convincing solution to this convergence. Generation ships spread the burden across multiple lifespans, but introduce the additional challenges of onboard reproduction, child rearing, education, and the psychological horror of being born inside a machine you did not choose to inhabit and cannot leave. Suspended animation, if it were achievable, would reduce but not eliminate the biological exposure, since hibernating bodies would still absorb radiation, and the hibernation hardware itself would require maintenance by someone, meaning at least a skeleton crew must remain awake and subject to all the degradation described above. Fast transits reduce the total exposure duration, but increase the radiation intensity per unit time due to relativistic effects on the interstellar medium and the blue shifting of galactic cosmic ray energies at high velocities. Every proposed path through the problem leads back to the same fundamental constraint. Human biology was shaped by 4 billion years of evolution on a planet with a thick atmosphere, a strong magnetic field, a 24-hour light cycle, a rich sensory environment, a functioning ecosystem, and an open horizon. Remove all of those things simultaneously, confine the organism inside a metal container, bombard it with radiation that its biology has no defense against, eliminate every external stimulus that its psychology depends on, and then ask it to perform at peak cognitive and social capacity for decades without interruption. The organism cannot do it. Not because it lacks courage or willpower, but because its hardware was not built for these conditions, and no amount of training can override the physical damage that the environment inflicts. But there is a final and most disturbing dimension to this problem. Everything described so far, the engineering decay, the biological damage, the psychological erosion, does not merely add together, it multiplies, and the longer the mission succeeds in continuing, the worse the multiplication becomes. There is a moment in every interstellar mission concept, somewhere between the engineering specifications and the mission timeline, where the math turns hostile. Not the propulsion math. That was always hostile, demanding energy budgets that exceed civilization scale output. The survival math. The calculation that tracks what happens to a closed system and the biological organisms inside it when both are subjected to continuous environmental assault for timescales measured in human lifetimes. This is the math that most interstellar discussions avoid, because the answer it produces is not merely discouraging, it is structurally cruel. The longer an interstellar mission succeeds in continuing, the harder it becomes to keep succeeding. Success does not build momentum, it builds burden. Everything described so far, the engineering decay, the biological erosion, the psychological disintegration, does not merely coexist inside the vessel. These processes interact, they feed into each other through loops that tighten as the mission progresses, creating a compounding failure dynamic that no single engineering solution can break. This compounding is not a design flaw that better technology will eventually eliminate. It is an emergent property of confining fragile biological organisms inside a degrading mechanical system within an actively hostile environment for durations that exceed the design lifetime of every component involved, including the organisms themselves. Trace the loops. A crew member whose prefrontal cortex has sustained cumulative radiation damage over 15 years of transit makes a calibration error while servicing the water recovery distillation assembly. The error goes undetected for 72 hours because the monitoring software relies on a sensor whose accuracy has drifted beyond acceptable tolerance due to radiation degradation of its semiconductor substrate. During those 72 hours, the distillation membrane is exposed to conditions outside its operating parameters, accelerating the fouling that was already reducing its efficiency. When the error is finally caught, the membrane must be replaced. The replacement membrane comes from a stockpile that has been stored for 15 years in the same radiation environment, and its polymer structure has already begun to degrade in storage. It functions, but at roughly 85% of its original specification. The water recovery rate drops another fraction of a percentage point. The cumulative water deficit grows. The crew adjusts by reducing water allocation for hygiene, which increases the microbial load on surfaces inside the habitat, which increases the demand on the air filtration system, which accelerates filter consumption, which draws down another finite consumable reserve, one error, one degraded sensor, one aging membrane, and the ship is measurably worse off than it was 3 days ago, in ways that affect multiple systems simultaneously and that cannot be fully reversed. Multiply this sequence by thousands of similar interactions occurring across hundreds of subsystems over decades of operation, and the trajectory of the mission becomes clear. The vessel does not decline in a smooth, predictable curve. It declines in a series of small cascades, each one triggered by the interaction of multiple degradation pathways, each one leaving the ship slightly less capable of absorbing the next cascade. The intervals between cascades shorten as the mission continues, because there are more degraded components capable of triggering them, and fewer reserves available to absorb their effects. Engineers call this phenomenon cascading failure coupling, and it is the reason why complex systems in harsh environments tend to fail not gradually but in accelerating waves. The ISS avoids this pattern because failed components are replaced with fresh hardware from Earth before the cascading interactions can develop. An interstellar vessel has no such relief valve. Every cascade propagates through the system and leaves permanent damage. The ship accumulates scar tissue, functional but diminished systems held together by improvised repairs and reduced operating margins. Each scar makes the next injury more likely and more consequential. The crew's role in this dynamic deserves its own examination, because they are not passive victims of the ship's decline. They are active participants in a feedback loop, where their own degradation directly accelerates the ship's degradation and vice versa. A healthy, well-rested, cognitively sharp crew can detect developing problems early, before they cascade. They can perform preventive maintenance that extends component lifetimes. They can improvise creative solutions to novel failure modes. They can resolve interpersonal conflicts before those conflicts degrade team coordination. In the early years of the mission, the crew functions as a buffer against cascading failure. Their competence absorbs shocks that would otherwise propagate through the ship's systems. But as radiation accumulates in their neural tissue, as confinement erodes their motivation and emotional stability, as sleep deprivation becomes chronic, as the sameness of the environment grinds away at their attentional capacity, the crew's ability to function as that buffer diminishes. They detect problems later. They perform maintenance less precisely. Their improvised solutions carry higher risk of introducing new failure modes. Their interpersonal conflicts consume time and cognitive resources that should be directed towards ship operations. The buffer thins. The cascades propagate farther. The ship degrades faster. And the faster degradation of the ship increases the workload, stress, and exposure that are driving the crew's own decline. This is the compounding spiral at the heart of interstellar survival. It is not one problem. It is the interaction of every problem with every other problem, mediated through the closed environment of the vessel. No system fails in isolation. No degradation pathway operates independently. The ship and the crew form a single coupled system, and that coupled system is being subjected to sustained environmental stress that drives both halves toward failure simultaneously. The cruel mathematics of this coupling dictate that the system deteriorates faster than either half would deteriorate alone, because each half's decline accelerates the others. Generation ships are often proposed as the solution to the biological time limit. If no single human lifespan is long enough to complete the journey, simply design the vessel to support multiple generations born and raised aboard during transit. The concept is elegant in abstraction and horrifying in detail. A generation ship must do everything an ordinary interstellar vessel must do, and simultaneously function as a self-sustaining civilization. It must educate its children, maintain a functioning economy, preserve technical knowledge across generations without universities or libraries, and manage reproduction and genetics to avoid inbreeding in a small founding population. And it must accomplish all of this inside a machine that is aging and degrading around its inhabitants. The psychological burden on generation ship inhabitants would be qualitatively different from anything in human experience. The founding generation chose to board the vessel. They carry the memory of Earth, the open sky, the ocean, the feeling of wind. They chose to sacrifice those things for a mission they believed in. Their children did not choose. They were born inside a metal cylinder they cannot leave, Surrounded by recycled air they have never known to be anything else. Educated about a destination they will never reach, and told that their purpose is to maintain a machine and produce the next generation of maintainers. Their grandchildren face the same reality, further removed from any cultural memory of planetary life, maintaining systems whose original design logic may have been partially lost through imperfect knowledge transfer, and experiencing the accumulated psychological effects of a social structure that exists solely to serve the vessel's survival. History offers no parallel for this social arrangement. Every human society that has ever existed, no matter how isolated, had access to the natural world. Seasonal rhythms provided temporal structure. Agricultural cycles provided purpose. Open landscapes provided sensory richness and the psychological relief of spatial freedom. A generation ship offers none of these. Its inhabitants live in a world where every surface is artificial, every sound is mechanical, every meal is processed from recycled biomass, and the horizon is always a wall. The psychological toll of this environment across multiple generations is not merely unknown. It is unknowable from current data, because no experiment has ever confined human beings under such conditions for durations exceeding a few years, and all such experiments allowed participants to leave if their psychological distress became severe. Suspended animation is the other commonly proposed biological solution. If the crew can be placed in a state of reduced or halted metabolism for the duration of transit, the psychological burden vanishes, and the biological exposure to radiation is reduced, though not eliminated, since ionizing radiation damages tissue regardless of metabolic state. The concept is appealing. It is also, by current scientific understanding, not achievable for humans. No method of inducing long-term suspended animation in mammals has been demonstrated that does not result in severe cellular damage upon revival. Cryogenic preservation causes ice crystal formation that ruptures cell membranes. Vitrification, the process of cooling tissue so rapidly that it solidifies without crystallizing, has been demonstrated for small tissue samples and in limited animal organ experiments, but scaling to intact human organs remains unproven, and whole organism vitrification for any mammal has never been achieved. Chemical torpor induction has been explored in animal models, with some promising results in rodents, but scaling these approaches to human physiology over timescales of decades rather than hours or days remains far beyond current capability. Even if suspended animation were achievable, it would not solve the interstellar survival problem, it would transform it. The hibernating crew does not maintain the ship. Someone or something must. Either a rotating skeleton crew remains awake, subject to all the radiation, isolation, and maintenance burdens described previously, but with a smaller team and therefore a higher per-person workload, or the ship must maintain itself autonomously through robotic systems that must function without human oversight for decades. Autonomous maintenance requires artificial intelligence and robotic manipulation capabilities far beyond current technology, and those systems themselves are subject to the same radiation, degradation, mechanical wear, and software corruption that afflict every other system on the vessel. The maintenance problem does not disappear when the crew sleeps. It is merely transferred to a different set of systems that face the same fundamental constraints. And then there is the revival problem. After decades of hibernation, the crew must be successfully revived, reoriented, and brought to full cognitive and physical function in time to perform whatever tasks the arrival phase demands: orbital insertion, deceleration maneuvers, system diagnostics, and potentially landing operations. If the revival process is imperfect, if even a small percentage of crew members suffer neurological impairment from the hibernation itself, or from the cumulative radiation absorbed during decades of unconscious exposure, the mission arrives at its destination with a crew that may not be capable of completing the mission's objectives. The entire transit was for nothing. The ship reached the star, but the crew inside it was destroyed by the journey, not in a single dramatic moment, but through the slow, patient accumulation of damage that defines everything about interstellar space. This is the cruelty that the title of this video describes. Reaching interstellar space is an engineering challenge. It is bounded, definable, and in principle solvable. You need enough energy, applied in the right direction, for long enough. The challenge is immense but singular. Surviving inside interstellar space is not a challenge, it is a condition. An ongoing, open-ended, compounding state of deterioration that begins the moment the mission starts and does not end until the mission does. There is no threshold to cross after which survival is achieved. There is only the next day, and the next, and the next. Each one slightly harder than the last because the ship is slightly more worn, the crew slightly more damaged, the reserves slightly more depleted, and the margins slightly thinner. The public narrative of interstellar travel places the drama at the beginning. The heroic launch, the daring acceleration, the bold leap into the void. The reality places the drama everywhere except the beginning. The beginning is the easy part. The drama is the 10,000th identical morning inside the same cabin, with the same faces, breathing the same recycled air, eating the same processed food, checking the same systems, finding the same slow drift toward failure, and knowing that tomorrow will be the same but marginally worse. The drama is the realization, somewhere around year 20, that the ship's water recovery efficiency has declined to a point where rationing must begin, and that the rationing will never end, only tighten. The drama is the diagnosis, in year 30, of a crew member with radiation-induced cognitive decline severe enough to remove them from maintenance duties, shifting their workload to an already overtaxed team. The drama is the bearing failure, in year 40, of a centrifugal gravity drum that cannot be repaired because the replacement bearings degraded in storage, and the crew must choose between living without artificial gravity and the accelerated bone loss that follows, or attempting a repair with improvised materials that may fail catastrophically. None of these dramas are cinematic. None of them would make a good movie trailer. They are the quiet, grinding, unglamorous reality of what it means to keep a closed system alive inside an environment that is constantly trying to kill it. And they are the reason why surviving interstellar space is worse than reaching it, because reaching it is a problem you solve once. Surviving it is a problem you solve every single day, with diminishing resources, diminishing capacity, and diminishing hope, for as long as the mission continues. There is a tendency, when confronting problems of this magnitude, to invoke future technology as a universal solvent. Perhaps future materials will make cosmic ray shielding trivial. Perhaps self-repairing nanotechnology will eliminate the maintenance burden. Perhaps neural interfaces will provide the sensory richness that confined human minds require. These are not unreasonable hopes. Technology has repeatedly achieved things that prior generations declared impossible, but hope is not engineering. And the specific challenges of interstellar survival are not merely difficult versions of problems we have already solved. They are fundamentally different categories of problem that emerge only at timescales and distances that human engineering has never operated at. The gap between current capability and interstellar requirement is not a gap that incremental improvement will close. The ISS achieves partial life support closure with continuous resupply, constant ground support, regular crew rotation, and a mission duration of months per crew. An interstellar vessel requires near-total life support closure, with zero resupply, zero external support, no crew rotation, and a mission duration of decades to centuries. The difference is not tenfold or hundredfold. It is a difference in kind, like the difference between swimming across a pool and swimming across an ocean. The skills are related. The challenge is not. This does not mean that interstellar travel is impossible. It means that interstellar travel is not primarily a propulsion problem. It is primarily a survival problem. And the survival problem will not be solved by building faster engines. It will be solved, if it is solved at all, by achieving breakthroughs in closed system ecology, radiation biology, material science, autonomous maintenance, and human psychology that are as profound as the breakthroughs in propulsion that most people focus on. The engine gets you there. Everything else keeps you alive. And everything else is harder. The honest assessment of where we stand today is sobering. We have not demonstrated closed-loop life support that can operate without resupply for more than a few years in any environment. We have not developed radiation shielding that can protect a crude habitat from galactic cosmic rays without prohibitive mass penalties. We have not solved the psychological effects of permanent confinement on human beings. We have not built mechanical systems that can operate for decades without maintenance by trained human hands. We have not created autonomous repair systems capable of diagnosing and fixing the range of failure modes that a complex vessel would experience over multi-decade timescales. Each of these gaps represents a fundamental unsolved problem, and an interstellar mission requires solving all of them simultaneously. The stars are not going anywhere. They will burn for billions of years, patient and indifferent, while humanity struggles with the question of how to reach them without dying on the way. The temptation is to focus on the romantic half of that question, the reaching, the crossing, the arriving, because it is dramatic and inspiring and feels like progress even when it is only theoretical. The harder, less glamorous, more important half is the staying alive. The daily, grinding, compounding work of keeping fragile biological organisms functional inside a degrading mechanical shell within an environment that offers no shelter, no resources, no mercy, and no end. Interstellar space is not a destination. It is a condition of absolute isolation, continuous radiation exposure, total resource limitation, and relentless systemic decay. Entering it does not represent the culmination of a mission. It represents the beginning of the mission's hardest phase, a phase that lasts not for the dramatic minutes of launch or the tense hours of orbital maneuvers, but for the entire remainder of the transit, measured in decades of unbroken endurance, against an environment that punishes every weakness and rewards nothing. The launch is the photograph. The transit is the life. And the life is harder than the photograph could ever capture. If humanity does eventually cross the interstellar void, it will not be because we built an engine powerful enough to get us there. It will be because we learned how to sustain a tiny, closed pocket of Earth, air, water, soil, medicine, sanity, and hope, across distances so vast and timescales so long that the act of maintaining it became the single greatest achievement of our species, greater than the engine, greater than the launch, greater than the arrival, the act of simply continuing to exist, day after day, inside a machine surrounded by nothing, for longer than any civilization has ever sustained any single endeavor, against an environment that does not care whether we survive or not. That is what it means to survive interstellar space. Not a single victory. An endless war of attrition against entropy itself, fought with failing tools, fading minds, and finite supplies, inside a vessel that is simultaneously the only home you will ever know and the thing that is slowly killing you. Reaching the stars sounds like triumph. Surviving the space between them sounds like something else entirely. Something quieter, something harder, something we have not yet proven we are capable of. And until we confront that truth honestly, every conversation about interstellar travel is starting with the wrong question. We keep asking how we get there. We should be asking how we stay alive after we do.